This is SCANS, a soft curvature and spectroscopy gripper for in-hand material differentiation. We embedded optical sensing components in a soft robotic finger to achieve curvature estimation and material sensing. We validated these features by grasping numerous objects of different materials while recording both the pre-touch and in-hand spectral signals, along with the curvatures of all three fingers. Each finger can be individually controlled and sensed from, and is self-contained aside from the spectrometers and cables. Each finger contains a cast silicone bladder that is enclosed by a flexible exoskeleton 3D printed out of TPU. The bladder is pneumatically actuated and the end is sealed with a clamp. The cross-sectional shape of the finger and the flat pad at the bottom enable constant curvature bending about one axis when actuated. The optical sensing components are housed in the bottom pad and are embedded during the 3D printing process. Light is passed in through these components with the bulbs in the clamp, and the fiber optic cables are connected to the output ends through these connectors. The embedded fibers are composed of a U-shaped waveguide that is used to sense curvature. Then there are two additional fibers that allow for material sensing. To accomplish the curvature sensing, light is passed in through one end of the waveguide. During actuation, the waveguide deforms and the light intensity loss is measured by a spectrometer connected to the other end, before curvature is estimated through a linear regression model. For material sensing, light is passed in through one fiber and exits perpendicular to the finger through the prism. The reflected light then enters the neighboring prism and fiber and is sent through a fiber optic cable to two spectrometers, which then collate the total spectral reflectance. We tested and validated our gripper by performing pinch and caging grasps on objects of various sizes and materials. In this example, you can see the curvature of all three fingers and how the reflected spectral signal evolves over time. To ensure that a strong spectral signal is acquired, we only read the response from one finger and actuate that finger slightly before the other two to make good contact. The ambient response is the first distinct signal when an object isn't in the workspace of the gripper. As the gripper descends around the object, the pre-grasp response is shown, followed by the in-hand response once the gripper fully actuates. Among the various test objects, some of the most interesting differences were between the real and fake fruit, as seen here in the much larger pre-grasp and in-hand signals for a fake apple. We performed these same grasping experiments on a wide range of other objects. In summary, we presented an electronics-free soft robotic finger with integrated optical sensing components for curvature estimation and material sensing. Thank you for watching.